Now I will explain the general properties of gases. First, definite shape or volume. Gases assume the volume and shape of their container. This means that gas does not have its own fixed shape or fixed volume. Instead, it spread out to completely fill whatever container it is in. Second, particles are far apart. Gases are the most compressible state of matter. Because the particles are very far apart, gases can be squeezed into a smaller volume when pressure is applied. Next, particles move rapidly in all directions. Gases meet evenly and completely when they are confined in the same container. This happens because gas particles are in constant random motion, so they spread out and mix with one another very quickly. Lastly, low density. Gases have lower densities than liquid and solids. This is because the particles in a gas are much more spread out, making the gas lighter compared to the same volume of liquid or solid. Next, I will explain the units of pressure. A unit of pressure is a unit used to measure how much force is applied per unit area. Unit of pressure formula is defined as force divided by area. In other words, pressure equal to force divided by area, and force itself is equal to mass times acceleration. This is for example. Let's continue with the first question.
Here I want to answer the question. The pressure outside a jet plane flying at high altitude falls considerably below standard atmospheric pressure. Therefore, the air inside the cabin must be pressurized to protect the passengers. What is the pressure in atmospheres in the cabin if the barometer reading is 688 mmHg? So first, the formula is pressure equal to force divided by area. We need to identify conversion equal to 1 ATM equal 760 mmHg. We are going to convert the pressure from mmHg to ATM equal to 688 mmHg times 1 ATM divided by 760 mmHg. So the pressure in ATM in the cabin equal to 0.905 ATM. That's the answer.
And this is question number 2.
Next, the second question is, the atmospheric pressure in San Francisco on a certain day was 732 mmHg. What was the pressure in kPa? So, we have to identify the conversion first, which is 1 ATM equal to 760 mmHg equal to 101.3 kPa. So, we need to convert the pressure from mmHg to kPa. 732 mmHg times by 101.3 kPa divided by 760 mmHg. So the answer we got 97.9 kPa.
Now I will explain the gas law. Here we have 3 types of gas law, which is Boyle's law, Charles' law, and Avogadro's law. The first one is Boyle's law. Boyle's law states that when temperature is constant, the pressure of a gas is inversely proportional to its volume. This means if the volume decreases, the pressure increases and vice versa. Next, this is application of Boyle's law. Let's proceed to the question.
One of the sample question of Boyle's law application is as given. A sample of chlorine gas occupies a volume of 946 ml at a pressure of 726 mmHg. What is the pressure of the gas in mmHg if the volume is reduced at constant temperature to 144 ml? So, the formula is PV1 equal to PV2. So here P1 is 726 mmHg and the V1 is 946 ml and 144 ml is V. So we will get in bracket P1 is 726 mmHg in bracket 946 ml for V1 and divide by 144 ml for V. So P2 we got here 4,459.7 mmHg.
Next is Charles' law. Charles law tells us that when pressure is constant, the volume of a gas is directly proportional to its temperature. So when temperature increases, the volume also increases. And this is application of Charles law. Let's move to the next question.
Next, one of the sample questions of Charles law application is as given. A 1 liter steel tank is filled with a safety valve that opens if the internal pressure exceeds 1.00 times 10 power of 3 torque. It is filled with helium at 23 degrees Celsius and 0.991 atm and placed in boiling water at exactly 100 degrees Celsius. Will the safety valve open? So we can use Gay-Lussac's law, which is P over T1 equal to P over T2. So we got here P2 equal P1 times by T2 over T1. So we can write here P2 equal to 0.991 atm times by 373.15 K divided by 266.15 K. So the answer we got P2 equal to 1.248 atm.
Another important law is Avogadro law. It states that equal volume of gases at the same temperature and pressure contain the same number of molecules. This means volume is directly proportional to the number of moles, and this is application of Avogadro law. Let's proceed to the last question.
The last sample question of Avogadro law's application is a scale model of a beam rises when it is filled with helium to a volume of 55 dm cube. When 1.10 mole of helium is added to the beam, the volume is 26.2 dm cube. How many more grams of helium must be added to make it rise? Assume constant T and P. So first, the formula is V1 over N1 equal to V2 over N2. Added all the variable from the question into the formula, which is the formula is N2 equal to N1 times V2 over V1. So equal 1.10 mole times by 55 dm cube divided by 26.2 dm cube, and we got the answer is 2.312977 mole. Next, we need to find additional moles of helium needed, which is N2 minus N1 equal, we got 2.312977 mole minus 1.10 mole, and we got the answer is 1.212977 mole. Lastly, we need to convert into grams. The formula is the change in mass equal to delta N times by molar mass. So we got 1.212977 mole times by 4.00 g mole, and the answer is 4.85 grams.
The ideal gas equation combines several gas bonds into one, which is PV equals nRT. We can see that P for pressure, V for volume, N for number of moles, R for gas constant, and lastly T for temperature. In chemistry, it is commonly used to calculate unknown gas properties in experiment and chemical reaction. Standard temperature and pressure, known as TP, is a reference condition used in chemistry. We can see that there are three things that are important in STP. First, standard temperature. Second, standard pressure. And lastly, at STP, 1 mole of any ideal gas has a volume of 20 to 142 liters. Density of a gas can be calculated. Use the formula D equals Pm over RT. Molar mass of a gas can be calculated. Use the formula M equals dRT over P.
Stoichiometry is the study of the quantitative relationship of gases involved in chemical reaction. It focuses on how the amount of one gas is related to the amount of another gas in a reaction. These calculations are based on balanced chemical equation and often use the ideal gas equation. PV equal nRT at the same temperature and pressure. The volume of a gas is directly proportional to the number of moles. Gas stoichiometry is commonly used to calculate the volume, mass, or number of mole of gases product or consumed in reaction, especially in laboratory experiment and industrial process. Dalton law of partial pressure states that the total pressure of a mixture of gases is the sum of the partial pressure of each gas in the mixture. Each gas behaves independently and contributes its own pressure, known as partial pressure. The partial pressure depends on the number of mole of the gas present. This law is useful in understanding gas mixture as oxygen cylinder and breathing gases used in scuba diving. Mole fraction describes the proportion of each gas in a mixture. It is defined as a ratio of the number of mole of a gas to the total number of mole of all gases. Mole fraction has no limit and is represented by the symbol G. The sum of all mole fraction in a gas mixture is always equal to 1. Mole fraction is closely related to Dalton law because it is used to calculate the partial pressure of a gas by multiplying the mole fraction by the total pressure.
Hello, my name is Aileen Sophia and I'm from AS1241C, and today I'll be covering the subtopic Graham's law, diffusion, gas motion, and real and ideal gases, and also molecular speed. So let's go through what is Graham's law. Graham's law states that the rate of diffusion or the diffusion of a gas is inversely proportional to the square root of its molecular weight. So first off, what is diffusion? Diffusion is the process by which a gas escapes from its container through a tiny hole into an evacuated space. This means that it goes from a small space to the other wider reach of space outside. So for an example here, the picture given is a bottle of perfume, there is aerosol sprays, and also when you exhale. Diffusion is the gas molecules from a high concentration to a low concentration areas driven by the random motion of the particles. And also another example for diffusion is actually the steams coming out from the hot pot, maybe a boiling water. So from the boiling water inside a pot, which is highly concentrated into the air surrounding it, and the air is considered as low concentrated. So the steam went out and throughout the air. The rate of diffusion of a gas is inversely proportional to the square root of its molar mass, as it is shown inside the formula given. 1 over square root m means molar mass. And also the other formula given is rate to the first gas divided by the rate of the second gas is equal to square root m molar mass of the second gas divided by the m of the first gas, and also equals to time of the second gas divided by time of the first gas. Take a look to a question that which we can apply this formula. Calculate the ratio of the diffusion rates of helium and methane CH4. So first, we need to search for the molar mass. The molar mass is actually the RAM, which is the relative atomic mass that will be given, and by that we are going to divide it with 1 over with square root with the surge with the found molar mass, so that we can find the answer, which is 2.1. So, in the next slide, we're going to talk about the deviation of drum ideal gas behavior. So, according to the kinetic molecular theory, there are 5 assumptions. So, first, they are consist of tiny particles of negligible volume, and there are also intermolecular forces of attraction does not exist between gas particles. And for the next one is it is always in continuous random motion. It is aimless. It will go everywhere without any heat, any direction as it is. And for the fourth one, the gas particles are perfectly elastic, so it eventually bounces off to any types of surfaces. And for the last one, that the average of kinetic energy of gases directly proportional to the absolute temperature. So here we're going to talk about the assumptions that were made from the kinetic molecular theory versus with the real gas. So the assumptions said that particles have negligible volumes, but in reality particles were actually measurable in volumes. And also particles have no intermolecular forces, but eventually in reality particles have intermolecular forces in which they will combine themselves with other types of gases. And lastly, the behavior described by the PV equals to nRT by the ideal gas. But in reality, it is less valid in high pressure and also low temperature. And this part we're going to go through next. In the next slide, we're going to talk about the effect of high pressure in both the ideal gas and also the real gas. So the ideal gas stated that the particle volume are still negligible compared to the size of the container. But according to the real gas, it is stated that the particle volume is now significant compared to the size of the container. And also the particles are very close, intermolecular forces become more significant. In this slide, we're going through the effects of temperature onto gases. So, when the gases were to be in low temperature, it would decrease in kinetic energy, and it has almost none to the impact of intermolecular forces. It will move much more slower than before. So, if it was compared to when the gases were in high temperature, it will increase in kinetic energy, in which means the intermolecular forces became more significant and the movement of the gases actually increase. So the other things that we can analyze from which when the gas were exposed to high pressure and also the low temperature is actually the intermolecular distance is becoming much more smaller, and the volume occupied by the molecules were becoming more significant compared to which the volume of the container. And other stuff is total volume occupied by the gas is much more greater than the volume, and then it is predicted by the ideal gas law. And for the side for low temperature, it is the kinetic energy of the gas molecule decreases, and the molecules can no longer overcome the intermolecular attractive forces as it breaks down. And for the other thing is the gas liquefies, it is condensed into liquid form. So, there are other significant differences between the ideal gas and the real gas is the ideal gas stated that it is volumeless, whilst the real gas stated that it has finite volume. It has also the particles that takes up space, and also the volume of the gas is actually much more less than the volume of the container. And ideal gas also stated that it does not interact with each other, so it won't have been attracted to the intermolecular forces created, so it won't combine with another elements and another gas particles. But the real gas stated otherwise, the particles do attract each other. And lastly, for the ideal gas stated that the molecules would travel in straight lines, but the real gas stated that the paths would curve to the attractions between the molecules. So it was eventually be pulled and then it will bond with other particles involved. And lastly, for the very last subtopic that I'll be covering today is about the molecular speed. So the molecular speed stated that although the molecules in a sample of gases have an average kinetic energy and therefore an average speed, the individual molecules move at various speed. They exhibit a distribution of speed. From what it is stated that we can do a comparison between a lighter gas and also the heavier gas when it is at the exact same temperature, in which the lighter gas moves much more faster and at the average speed, whilst the heavier gas move much more slower compared to the lighter gases.